Our topic today is enriching uranium, beneficiation and specific applications for civil and military use. And with us, Gabriel Lynch Murphy, postdoctoral nuclear materials scientist, PhD researcher in fuel cycle research. And this is me, the moderator, Armando Cabaño. Let me remove here. And good afternoon, Gabriel. Welcome.
Thank you, Amanda. It's nice to be back again to talk about very topical things in nuclear world again.
Yeah, very interesting topic. Everyone is talking about these issues that nowadays. Gabriel, let me ask you if you can start with the steps of uranium ore beneficiation before the enrichment, the very
Yep.
beginning of the process. Could you please explain us how does it work?
Yeah, sure, with pleasure. So of course, before we make nuclear fuel or do other things with nuclear material, we have to start with the basic ore material, and this is often finally in forms of uranium ores. And so there are a variety of uranium ores found throughout the world. The countries that have the highest stockpiles, well, the highest natural amounts of uranium ore, you could look at countries like where I'm from, Australia, also countries like Kazakhstan, also within Russia and Canada, quite large amounts of uranium ore. So what's often done with uranium ore, so quite a large amount of uranium is actually found on the surface of the Earth. So a lot of sort of open cut mining is performed to extract uranium ore from the surface. After the uranium ore has been extracted, of course, this is normally occurring around, I understand, around 1,000 parts per million in the ore. Can be a little bit higher as well. So this is the grade that mining companies are typically interested in. So from there, they need to extract the uranium ore the uranium from the ore. So one of the main first steps is what's doing or one of the most common ways is doing sulfation-based roasting of the ore. And this is where you start converting the ore mineral into specific forms of uranium, so uranium sulfates, and other forms of uranium which are what are called leachable. You want to perform leaching. What leaching is essentially is you taking that ore after it's been baked in an oven, almost like baking a cake, and you wash it with water. As you wash it with water, the uranium just falls out and just dissolves out into this water, into this leachate. And once the leachate is out, you have this, what some people like to call it a pregnant leach solution. So you have an enriched solution with uranium. And from that, you then want to kind of separate it a bit further because you pull out a few other bits and pieces there too. So you want to precipitate this. And this precipitation process using sort of certain specific chemicals and control pH results in a cake-like product, very famously known as yellow cake. And so this is performed in countries often like Canada and Australia and Kazakhstan as the final kind of produced beneficiated product from the uranium mining process. That product is then often transferred or sold onto other companies before to perform things like uranium enrichment and also for fabrication of nuclear fuel or for nuclear materials. So that's kind of the shorthand of how kind of you start from uranium ore and go towards making yellow cake. And as the name suggests, it's quite yellow if anyone wants to Google it.
Yellow. Until this time is a normal mining process. I mean, there is no different risks or only environmental impacts and things like that. Exactly the same of mining other
Largely,
minerals.
yes, yeah. So this is still radioactive. Uranium is a radioactive material naturally occurring in nature, and so you call this in specific terms norm radiation, which is naturally occurring radioactive materials. So uranium is a relatively potent alpha emitter. So it's there is danger to inhalation. So when you are at a uranium processing plant, a uranium mining site, there is still dangers associated with exposure to uranium, but the exposure is mainly related to inhalation. But at the same time, too, there are kind of the regular dangers as well, too. But in terms of high level radiation that arises in nuclear facilities like nuclear reactors, it is not the case, is not a comparable.
And from the yellow cake to ahead, I mean, is the process of enrichment? No, is the process of beneficiation first. How does it
Mm-hmm.
work?
So the next step after you have the yellow cake is then you want to convert it. So it depends on your process. So if we're just talking about, say, nuclear fuel fabrication, you have a choice in terms of what you want to do with your yellow cake. So in the end, you want to turn it into often a uranium fuel rod, a fuel pin. So I think you could show a picture I've showed you of UO2
Yeah,
pellets.
sure. Which one you have? Is
So
this one?
next one,
Next
I
one?
believe. Next one. Yeah, so this is the end product. So if anyone's ever wondering what nuclear fuel finally ends up like, this is it too. So this is uranium dioxide. And so they're very small little things actually, but they're stacked up together to make fuel rods. So the one on the back there, it's about 1 gram. It's an industry fabricated material. It can generate as much energy as around 140 kilograms of coal, despite only weighing 1 gram. So for this material, this is kind of what nuclear fuel looks like. So this is the target what people often want for regular nuclear power reactors. So the question is, of course, so what's your choice of getting it there from the yellow cake? And the question comes to in terms of enrichment, because in nuclear energy, in nuclear fission, the key is you want to have a good amount of the isotope uranium-235. In naturally occurring uranium, so what is actually produced and mined as well, it only contains 0.711% natural uranium. Okay.
Mhm.
In a conventional power reactor, a light water power reactor, you want to have 3 to 5%. This is the magic enrichment number, between 3 and 5%. So you need to enrich from 0.71 to 3.5%. So you have to increase that amount. I would say, though, there are many reactors in the world that don't need that. You don't often need to enrich. So there's the famous example, what are called the CANDU reactors. These are nuclear reactors operated in Canada. These just function on natural uranium, so you don't even really need an enrichment process at all. You can take the yellow cake and proceed to the fuel fabrication directly as well. It depends on your reactor specifications, okay? But when we talk about processing the yellow cake, the next step is, if we're going to go down the enrichment route, is, as I say, we need to increase the amount of uranium-235 present. So the problem is, you're trying to increase the amount of uranium-235 present compared to the other isotope, uranium-238. So and there's also a bit of uranium-234, but let's just consider 238 and 235. In 238, we have 99.2%. With 235, we have 0.711, and we want more of that little one there too. And the difference between these two isotopes is that they only have essentially sort of, well, 3 neutrons in the structure as well too. So it's a very, very subtle difference at the atomic level. And so it's very, very difficult to separate. So in many areas of chemical engineering and process engineering, when you want to separate out chemicals, you can use a lot of different tricks in terms of the chemistry of the materials. We can compare the weight or the density of the materials. But this is very, 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 very subtle. As I say, only 3 neutrons different. And so the key that was first developed, and the key main method that was used today, is called gas centrifusion activity. And the idea is, you take this yellow cake that I described, and then you convert it into what is called UF6. And of course, if people are looking at the news about Iran and places, these are the facilities that were targeted. They were facilities that possessed uranium UF6. And the key of UF6 is actually a gas. So when I talked before about yellow cake, it's actually a solid, but you can turn it into a gas. So you take the yellow cake, you kind of essentially do some special kind of sintering and chemical conversions to add fluorine into the system, and you convert it to UF6. And now you have a gas product. You capture that gas product, and now with the gas, you can actually then separate it based on the densities. So if you show one of the pictures I sent you before, Amando.
Sure. Let me see. Which one is
So
that? Maybe this one?
no, that one's quite good. It's a little bit pixelated, but it kind of gives the idea as well too. So this is actually from
Sorry, this one. Yeah.
Yeah, all good. So this is actually from the company Urenco. So Urenco is a very well known in the nuclear sphere chemical conversion company, where they actually produce enriched uranium and nuclear fuel for civilian purposes. And the idea is, as you can kind of see from this diagram, is the uranium F6 is pumped into these centrifuges, and it's essentially spun around in a circle. It's centrifuged around and moved around. And so the difference in density between the UF6 that contains uranium-235 and the majority part that contains uranium-238 will start to drift. So the uranium-235 will start going more towards the center of the centrifuge, whereas the 238 goes towards the outside. And you start to get a separation based on different isotopes as well. But as I say, it's not an easy process, because the difference between these two isotopes is only 3 neutrons. It's very, 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 very subtle. So it's not an easy form of separation. It takes time. It takes a lot of recycling. So you have to optimize this process and do it around and around. So it takes time to actually perform and do. And the end product is you'll start generating a more enriched product, but it becomes harder and harder and harder the more enriched you want it to be. So achieving regular kind of light water reactor fuel levels, as I said before, between 3 to 5%. I would not say it's easy, but it is much more attainable than going for the higher enriched amounts.
Mhm, mhm. What type of plants, manufacturing plants, are they similar to what? A, a normal plant, a refinery, or oh, hold on, he is coming back soon. Sorry, technical problem with Gabriel, but probably he is coming back very soon. Uh-huh. Where is Gabriel? He's not here yet. Uh-huh. Let's wait for him. Thank you, Mr. Kawaguchi, for the participation here with us. It's a great pleasure, and thank you for the contribution. Gabriel is still off. Oh, he's coming back.
Sorry, Mando.
Yeah, no problem. Let me show that we have a contribution from Mr. Kawaguchi. He's a famous journalist in Brazil. Thank you and welcome, Kawaguchi. But yeah, I was asking you, Gabriel. Let me return here. Sorry, yes. Uh, uh, about the type of plants for this purpose of beneficiation and enrichment, are there like refineries? How are they seem like to?
Yeah, great question. So, look, famously, uranium enrichment plants are quite large. These centrifuge, I think there was another photo I had as well before. It might be a little bit dangerous sharing it, might crash again, but there was a photo there I gave you from Urenco showing what the centrifuges actually look like. And when a uranium enrichment plant is built, it is quite large. And by large, I mean it's a sizable refinery building. And historically, what this meant when it comes to actually monitoring non-proliferation and not monitoring people using enrichment plants safely, you can see these plants from space using satellite imagery. And so Overwatch organizations, specifically the International Atomic Energy Agency, for a long time could keep an eye on global nuclear operators based on the size of these facilities. And in the very topical case of Iran, to hide these facilities, you have to go underground. And this is difficult from an engineering sense because these are very, 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 very large facilities. So, historically, these are very big facilities that can be readily monitored, particularly with satellite imagery. And this is a big ongoing topic from places and people at the International Atomic Energy Agency, among others.
Perfect. You mentioned three countries, Kazakhstan, Australia, and another one that I don't remember now, that are the focus for mining process. I suppose that Brazil has mining process for uranium too.
Yep.
I'm not totally sure. But it's only for the mining process. And the technologies for the beneficiation and enrichment, which countries are the most important ones?
Sure. So when it comes to the actual enrichment, the bigger country, the biggest operator is a country like the United States, because they have a big, broad history in the nuclear sector. France, definitely, because in France, they have a very, very large nuclear energy sector that's currently operating. Germany, historically as well, too, but Germany is now in a shutdown phase as well, so activities are much more limited. You can look as well at countries like Japan, because they have a very large nuclear energy sector as well, too, and also China. So often there is a bit of a somewhat of a physical line between the countries that do mining operations like Kazakhstan and Australia, and also the countries that then operate the power reactors. And those countries there too, that often actually have their own civilian nuclear sector, they tend to also have their own kind of fuel manufacturing and enrichment processes.
The dominating technologies to beneficiation and enrichment is not for all countries or type of countries, normally developed countries. But the point is the limit to make these things to the civil use energy and to the military use. How does it work, these limits to one thing and the other thing?
Sure. So it's all about, in the end of the day, the use of it. So for enrichment, the point of enrichment is you want to have more uranium-235. It's more fissile, and by more fissile, it generates more energy. And And so you ask yourself, okay, why do you want to generate more energy? So for a nuclear power reactor, you want to get to up to around 5% because you want to be able to sustain criticality. You want to have the fission reaction proceed spontaneously, so it continually generates energy, controlled, of course, by controller rods, etc. But you want it to be continually flowing forward as well too. But there are also applications where you say, okay, this is a good amount of energy for civilian use, so for regular electricity consumption. But there are some areas where you say, well, I want to actually have a lot more energy produced. And this is not talking about weapons, but we're talking about kind of systems. So a good example is also the military, but not military weapons, but military propulsion. So for instance, in the United States military, in the French military, and also the Brazilian military actually as well too, a lot of them involved in nuclear reactors that are in ships, in both submarines and also aircraft carriers. And the idea behind these vessels is they don't want to refuel. They want these machines to stay out in the ocean, continually operating, because in the case of submarines, they want to be quiet. They don't want to come up to the surface to refuel. They want to stay under the ocean, not detected. And so therefore, you need an energy source that lasts and sends out energy for quite an extended amount of time. And so in this instance, nuclear engines using nuclear power reactors, which have a fuel source that gives out a lot of energy, are more desirable. So when you look at these examples of these nuclear submarines and also aircraft carriers, they operate on nuclear reactors that have a much higher amount of enriched uranium. This is much higher, often between sort of 20, 30, 40, 50, 60, 70, sometimes to 90% potentially as well too. And the idea is the concentration of the uranium-235 is higher, it sends out more energy, and therefore from that it's more efficient. And for many of these machines, what's so remarkable about them is they don't ever need refueling. So many of these machines are designed such that they never need to have a resupply of uranium, a resupply of fuel for 20 to 30 years. It's essentially once the fuel goes in, it stays in. But for this, as I say, they need to have a high amount of enrichment. As a consequence, people also think about the application towards space exploration as well too, because the energy density is just so high and you minimize the need to do activities like refueling.
Good, good. For the civil use, nuclear energy is very efficient, and the most important problem, in my view, that's the time to construct a power process. How do you see the use for civil, and why Germany is closing, is leaving the energy source?
Yeah, sure. So in terms of construction times, you know, it varies historically in many ways. So if you look at the dawn of the nuclear age in around the 1950s, when it really started picking up after World War II, reactors were built quite rapidly. You can find some famous reactors, say in Belgium, of reactors. Some are still operating today that were constructed within a year, and they're still operating too. But as time went on, there was more kind of oversight came in terms of safety. And in many ways, this was warranted because these are very dangerous facilities. Okay, when the nuclear is a very efficient, nuclear energy is a very efficient process. It has a lot of benefits, but the potential harm of accidents and instances is quite damning, is quite bad, of course. And so the famous examples is things like Fukushima and Chernobyl. These are the few, and also 3 Mile Island to a smaller extent. These are the main international nuclear instances that happened. There was a lot of fear generated when these incidences happened, and of course, many countries reacted in kind. When, for instance, Chernobyl first happened, this instigated a big change in how nuclear reactors were built and how they were actually overwatched in a way. So in many nuclear reactors, if people have the opportunity or the luck to drive or be near a nuclear reactor, you often see these very domed shaped buildings, and these are called the containment buildings. And these are designed both to protect the reactor in case someone tries to drive a plane into them, but it's also designed to stop the release of nuclear material. So these became very popular and mandated essentially after things like the Chernobyl disaster. So this, of course, increases cost. But at the time when Chernobyl happened, it wasn't a huge still increase as well, because Chernobyl was in the 1980s. At the same time, countries like France were still rapidly increasing their amount of nuclear activity as well too, well into the 90s too. But as time went on as well too, more regulations came into effect. And of course, so they're very specific in terms of different countries. And so people often like to point to how expensive it can be to build a nuclear reactor, but it always depends on what country you're talking about. The United States is criticized a lot these days, or in the past, because of the time it takes for nuclear reactors to be built and the cost as well. And many people would say the regulatory side is quite overarching and sometimes a little bit sort of redundant as well. So and they argue then therefore maybe a more systematic and a more kind of efficient process. And this is what the current administration in the United States is pushing towards now too, is trying to kind of reduce the regulation in a safe way, but it allows a more efficient process. If you then look at countries like the United Arab Emirates, who recently constructed the last couple of years power reactors themselves, they were able to do this in approximately less than 10 years as well too, whilst following all international safety guidelines as well too. So sometimes there is a bit of overregulation, and also there's sometimes quite a bit of necessary and good regulation too. So it's kind of two mixes as well, which has increased the time.
Good point. Regulation dependence, yes. Let me ask you, please, you as a high-level professional in nuclear energy, how do you see the geopolitical issues that we are facing at this time in the world?
It's difficult in a way too, because nuclear has gone through these sways. So when we mentioned before about Germany shutting down its nuclear energy production route, this was done because after the Fukushima disaster, and the country decided that they no longer would pursue this, often on the reason in terms of, well, there was a fear and safety aspect as well. And the country then went down the line of investing more in gas. Then, of course, the Ukraine-Russian war broke out, and this then skyrocketed gas prices. And Germany came into a bad situation in terms of energy dependence on foreign sources and energy sovereignty. And so in the past, there was thought that, well, does nuclear really have a place? But what's really been highlighted in terms of, as we move towards cleaner climate targets, is the need also for not just CO2 reduction, but energy sovereignty. So you need to have energy sources which can be generated both in your country, you can attain the fuel within your country, and therefore you can help resist shocks that can come from essentially, international geopolitical states and situations. And this results then in many countries now investing more in nuclear. So you can look around the world in nuclear news. France is building more nuclear reactors. They were thinking of scaling back, and now they're increasing as well too. The Netherlands is increasing as well too. Poland is opting for nuclear in their future as well too. Belgium has reconsidered their future. They were considering turning off their power reactors, but now they've completely reconsidered this. Countries like Denmark and Italy, which said first that they want to be involved in nuclear, are also reconsidering. Even lately, the last week, Norway is opening committees into this as well, because the energy sovereignty found in nuclear energy, the fact is you can generate your own nuclear source often, or you can stockpile fuel, because the amount of fuel you need to power a reactor is not very large in terms of a bulk amount. And so often what did happen after the Fukushima disaster is many nations stockpiled fuel, and they just held onto it, and they can just use it well into the future. And so the storage requirement for fuel, not spent fuel, but fuel, is not so difficult. And that allows for energy sovereignty and then protects a nation's electricity production.
Perfect. Mr. Kawaguchi asking us, you, of course, how much enriched uranium should be to be used for fuel for submarine and vessels? And what the difficulties to build the nuclear reactor for this kind of vessels? Brazil is struggling to make for decisions.
Sure, that's a very good question. So it depends. It's always going to depend, of course, but it depends on the reactor type you want to use. So I know a little bit about the Brazilian situation, because Brazil has had some dealings with the French, and they're trying, to my understanding, is build reactor designs based on what the French have as well too.
But in the past was Germany, the sponsor for
Yeah, exactly. So often the case is many countries tend to focus on a design that suits them as well. So the Russians have had their design of nuclear reactors, the Americans have their design of nuclear reactors, and not many countries have been very keen to share their actual reactor design. And the reactor design is highly dependent on the fuel source, and the fuel source you opt to choose as well too. And so this depends therefore on your uranium fuel source as well. So when you're trying to actually acquire nuclear submarines based on foreign efforts, so in case of Brazil and actually recently like Australia, it can be difficult because it depends on who is helping you in this instance and if there are issues there as well too. So in terms of how much enriched uranium you need, so typically you can do submarines at 20%. So there are examples of 20%, but this then changes the fuel. So earlier we talked about the fuel type. I showed you actually work from where I work in Germany. So this is uranium dioxide. It's a regular kind of power reactor kind of model research material that I showed you. That's uranium dioxide. In many naval reactors, they use uranium metallic, which is a harder material to make, or they use kind of composite alloys of uranium with zirconium. You can also use things like uranium molybdides and nitrides. These are all different chemical forms of uranium, and therefore they change the enrichment process itself too. And so when you're using things like 20% uranium, what this often implies to the chemist, the nuclear chemist, is if you use 20%, this is probably a metallic-based form, which is a harder fuel to often process and develop, even though in terms of the enrichment, it's often lower and more safer and easier to oversight and handle too. Whereas if you go to more highly enriched uranium, say up to the 90%, you're working with uranium dioxide. And so things like uranium dioxide have a very good industry established process route. But the enrichment process is far more controlled because at these enrichment levels, we're starting to talk about potential proliferation towards weapons. So you can see it's kind of a balancing point of the technology towards designing the fuel material and also the enrichment point there too. So you often kind of have to know what is your fuel source. Can you manufacture your fuel source? Can you get a good amount of enriched uranium for this fuel source? And then it has to match your reactor. So you can see it's kind of 3 specific steps too. So if you're a nation that's already building your own submarines, has a domestic nuclear sector where you can fabricate fuel and enrich fuel, you're quite set. So France, Russia, the United States are all quite successful in this regard. For countries like Brazil, which are trying to enter the game, it's harder. They're relying on French or German assistance, and it's just a bit harder because there's only so much control over the fuel and the enrichment source.
And the interests sometimes are in conflicts because types of interest, of course, not only commercial, but of course geopolitical ones. Let me ask you my final point. Of course, you can bring more things if you want, but do you believe, only an opinion, and I'm not sure that you can answer this or not, Iran, the country Iran, has enough technology to make a nuclear weapon?
This is it's a $1 million question in a way that everyone's kind of asking at the moment too. And look, it's sometimes it's kind of like, what do you mean by a nuclear weapon is a short, bad answer, because people talk about dirty bombs for a long time. In a dirty bomb, you just need nuclear material and an explosive, and you can rain down radioactive material upon a population and cause a lot of harm. The explosive yield is nothing. It's a regular explosion, but this is still a harmful weapon in itself too. When it comes to fissile-based nuclear weapons, many people do believe at their enrichment levels they can do something. I mean, the science says that around 20% you can actually go towards making a fissile nuclear bomb. The power may not be as good as what's the conventional thermonuclear device, but it still can do extraordinary damage. In Iran, they're talking that they've achieved numbers in towards 60%. So in many ways, this is a threat in itself too. So look, the Iran situation is very difficult. And the reality is too, it's quite known that the oversight in Iran has been quite lost since around 6-7 years. And this is quite important because there is a need for civilian energy production, and Iran does have civilian-based nuclear energy. And it is important for them. This is what they want to pursue, and they're in their right to pursue this too. But at the same time, it's important to oversight them to make sure they're not using this for proliferation uses and weapon uses too. So look, in short, it's hard to say without being there because they keep things very, very, very quiet. But the direction they're going is, it does appear they are going towards a weapon state, or trying to go towards a weapon state, because as you may get from what I say, if you're going above 20% uranium, unless you're trying to build a nuclear submarine or an aircraft carrier with a very highly specialized nuclear reactor core, it's hard to find other potential options for what 60% enriched uranium with uranium-235 could be used for and above.
That's great. Did I forget any crucial point that you wanted to mention?
I mean, I guess one of the main things to mention quickly though is just the fact that in nuclear there is a lot of oversight and security when it comes to these processes. Organizations like the International Atomic Energy Agency spend a lot of time making sure nations follow correct procedure protocol to ensure against proliferation risks. And so people may have fear about nuclear weapons, but there are a lot of people working behind the scenes using advanced technology from satellite imagery to artificial intelligence and everything to make sure people are actually pursuing things for peaceful civilian purposes. So there are actual good, strong, peaceful benefits of nuclear energy and nuclear science.
Perfect. This is Gabriel Murphy. He is from Australia, but working in Germany. Thank you so much. It was a great pleasure.
Thank you, Amanda. It's nice to be here.
Bye-bye.
Goodbye.